Some AI research teams are working on something called causal inference, the process of discovering causal relationships from data. Causal inference involves complex statistical methods aimed at identifying which factors actually cause changes in outcomes as opposed to merely being associated with them. DAGs attempt to represent causal relationships, but they do so in isolation. They treat causality, time, and state separately. This separation creates a fundamental problem. In the real world, causality, time, and state are intrinsically linked. Instead of treating these elements separately, DADA X integrates causal relations, temporal relations, and state context. It's a holistic approach that captures the complexity of real-world systems. DADA X's unique ability to track causality sets it apart from approaches that infer causality. Rather than discovering causal relationships, causal tracking is about operationalizing them, taking predefined causal relationships as modeled in concurrent state machines and using them to drive real-time decision-making and control. At the end of the day, each of these agent models, causal activity models, is more powerful than a state machine. It's more powerful than a Markov chain, because the agent is truly concurrent. Markov chains are inherently sequential. They represent a system moving from one state to another, one step at a time. But in the real world, especially in distributed systems, multiple events often occur simultaneously. When Markov chains try to model systems with multiple components, they use what's called an interleaving approach. This limitation means Markov chains struggle to represent causal relationships between concurrent events. They can't capture how an event in one part of a system might instantly influence another part. And Markov chains typically lack an explicit representation of time. They model transitions between states, but not the duration of states or precise timing of events, crucial factors in concurrent systems. DADA X causal models, on the other hand, can represent and analyze multiple events happening at the same time, along with their causal relationships. This is vital in distributed systems where many things are happening in parallel. By using causal tracking, we ensure that every decision made by the system is based on an explicit understanding of the causal dynamics at play as defined by the agent model. This leads to greater precision, reliability, and responsiveness, especially in mission-critical scenarios.